Welcome to Ask and Learn.
In this problem, argon is compressed in a polytropic process, and we wish to calculate the work done and the heat transfer in the process. We assume here that argon is an ideal gas, since it is at a high temperature and low pressure relative to its critical point values, and the kinetic and potential energy changes are negligible. The properties of argon are its gas constant 0.2081 kilopascal meter cube per kg Kelvin. These are from our tables. And the specific heat at constant volume is 0.3122 kilojoule per kg Kelvin. Now, the system here is closed since no mass crosses the boundaries of the system. And we can write the energy balance equation as follows. E in minus E out, the energy in minus the energy out of the system, is equal to the change in energy of the system, delta E. And the energy into the system is 1 due to heat minus the boundary work, which is out of the system. So the negative sign is since the boundary work acting on the piston and the surrounds is out of the system. And this is equal to delta U, the change in internal energy of the system. And so we can write delta U as m CV times a change in temperature T2 minus T1. So before we can use this equation, we need to find this boundary work. So we'll use the boundary work relation for a polytropic process of an ideal gas. And we get the boundary work is equal to R times T1 over 1 minus N into P2 over P1 to the power N minus 1 over N, all this minus 1. So now we can substitute our values in here and find this boundary work. So R, and our values here in SI units, so we'll suppress the units, 0.281 kilojoule per kg Kelvin times T1, which is 283 Kelvin, over 1 minus N, where N is given as 1.2, into the ratio of the pressures, which is 800 over 120 over 0.2 over 1.2 minus 1. And hence we get the boundary work to be minus 109.5 kilojoule per kg. So this boundary work is negative since the gas of argon is compressed. So that's the boundary work out. So this energy is actually into the system, and the boundary work inwards is positive 109.5 kilojoules per kg. So this is actually the specific boundary work, little w, and this is the specific boundary work into the system, or the boundary work per unit mass. So that's kilojoules per kg. Now the temperature of the final state we can find as well. So the final state has temperature T2, which is equal to T1 into P2 over P1, the ratio of the pressures, to the power, again, N minus 1 divided by N. So we substitute our values in here. That's 283 Kelvin into the ratio of the pressures, 800 kilopascals over 120 kilopascals to the power of 0.2 over 1.2, where N is 1.2. And hence we get the final temperature of the gas to be 388.2 Kelvin. Now that we have our temperature of the final state, we can go back to the energy balance equation and calculate the heat in. So the specific internal energy, the specific heat transfer Q in is equal to the specific boundary work, the boundary work per unit mass, WB out plus, so we basically divided the entire equation here by M. So Q over M is small q and W over M is small w. So this is equal to CV T2 minus T1. We see the M vanishes. So now we can calculate this heat transfer since we have all these values. So this is equal to minus 109.5 kilojoules per kg plus CV to 0.3122. We'll suppress the units there, to a change in temperature of 388.2 minus 283, and that's Kelvin. So we get the heat energy in per unit mass to be minus 76.6 kilojoules per kg. And so that means that since this value is negative, the heat transfer is out of the system. And so this heat transfer is 76.6 kilojoule per kg.